Hey guys, welcome back. Today we're going to talk about wave speeds, which is how quickly a wave moves from one point to another. So, definition of wave speed is pretty self-explanatory. It's how fast does the wave move? How fast does that disturbance move from one location to another? So, a formula for that would just be the total distance that it travels divided by the total time that it takes to get there. So, since it's a speed and a velocity, it has the same unit that velocities have, v, or same symbol that is, a v, and the units would be normal velocity units, so usually meters per second. You could also talk about wave speeds in terms of miles per hour, miles per second, feet per second. Lots of other units are possible, but meters per second, the standard in the SI system. So I wanted to give you a couple speeds of waves that you ought to memorize. The speed of light, that is actually the speed of any electromagnetic wave in a vacuum. So when it moves through deep space where there's no other stuff around, it travels at this speed, 3 times 10 to the 8th. Written out, that'd be 300 million meters per second. And converted into a more familiar unit to us, that's 186,000 miles. Yeah, you thought I was going to say per hour, didn't you? No, 186,000 miles per second. So, just for some comparison's sake, the Earth here, Moon's out here. The Moon is over 200,000 miles away, and so that means that light gets there in just over a second. So this was evidenced when we went to the Moon back in the 60s. We orbited several times and eventually landed there. Radio transmissions were made. You could communicate back and forth via radio waves, but the closer they got to the Moon, the longer of a delay there was. So there's about a 1.5 second or so delay before they got the message on the other side, and that's because the radio waves traveled at the speed of light. Another wave speed that you ought to memorize is the speed of sound. Now, the speed of sound is a little trickier because sound varies a lot on what type of wave, what type of medium it travels through. So things like, is it through air? Is it through water? Is it through solid objects like brick or glass or something? But a good number to kind of memorize for when it travels through air is approximately 343 meters per second. So through colder air, it will move slower. Through faster air, where there's more molecule, or warmer air, where there's more molecules that are more energized around, the waves will move through a little bit faster. Through water, it tends to be much faster, on the order of about 5 times or so faster than on the air. But that also depends on the temperature of the water and whether the water's got salt in it and things like that. And through solid objects, sound can move even faster than that. So anyway, a couple questions to answer. First is just suppose you're at the baseball game, you're watching, you're an outfielder out there watching, and you see that the ball was hit. How long is it going to take for you to kind of hear the crack of the bat? So the overall equation is just a simple velocity one. Velocity is distance over time. And we're interested in how much time there is, so maybe I'll multiply by t and divide by v, and so I get that the time it takes is the distance away divided by the speed. And so the distance away is 75 meters, and the speed, in this case, it's sound is traveling towards us, and so the speed of sound is 343 meters per second. Unless we're told some reason doesn't believe otherwise, we'll just use 343. And so we can divide this out. Clear. Oops, gotta quit. There we go. So 75 divided by 343 is roughly 22 hundredths of a second. So that's noticeable. you'll see, and then a quarter of a second later, you'll hear the crack of the bat. So, now, an interesting question that was posed to me once is, suppose we were home watching the game live on television. So, when you're live on television, the signal has to get sent up at the speed of light up to a satellite and maybe back down to the antenna at my house. And then that gets transferred to my ear, and I'll hear that. Let's see how long that would take before I hear it. In order to pick up the sound, there's got to be a microphone nearby. A lot of times those microphones are, here's home plate, they're on the backstop over here. So let's say that might be 10 meters away. And so the sound, or the wave, has to travel as sound for 10 meters. And then it gets converted into an electrical signal and gets transferred as a light wave up 100 kilometers to the satellite, and then back down 100 kilometers. And then it'll eventually get to my TV. And suppose I'm sitting, I don't know, maybe 5 meters away watching the game. And the TV makes the sound, and that sound has to travel 5 meters to me. So let's calculate what this is. If it moves 10 meters as sound, 200 kilometers as light, and then another 5 meters as sound. So time is simply distance divided by speed. So 10 over 343. Here is a total of 200,000 meters. And it travels that distance as light, and so it travels at 300 meters per second. And then it travels again 5 over 343, because this is light, this is sound wave again. And so if I add those three things together, 10 over 343, 200,000 over 300 million, and then another 5 over 343. This says that I will hear it 0.04 seconds later. Now, I thought that was pretty remarkable the first time I heard it, that the outfielder will hear it 0.22 seconds, but I, by virtue of the fact that I've got a microphone hooked up a little closer, I will hear it only 0.4 seconds later, or 0.04, excuse me. So I'll hear it actually before the outfielder. Now, there probably is actually some time delay in here that I don't really know as it converts from sound to a light, and I'm sure there's some sort of a time delay in here, and maybe those delays add up to more than this difference, but the actual transmission of the signal doesn't take that much time. I've always wanted to go there and test this, maybe sit in the outfield with a radio and see if I could hear it via the radio faster than I could hear it in real life. I always wondered if maybe the outfielders could get a bit of a I don't know, cheat or jump by wearing a little radio on their ear or something like that, and see if they could hear it just a smidgen of a second faster. That would help them. But anyhow, thanks for listening, and be sure to tune back in next time as we watch and hear about wave frequency and how that is related to all these concepts.